Ladies and gentlemen, this is first of the series of nuclear lectures, series of the Strategic Vienna Institute. This is intended to be an information and education program. We know that everyone knows about and talks about the atoms and nuclear weapons and related technologies, but there is lack of understanding of various aspects. So this is an effort to share with you various features and the components of nuclear weapons technology to enhance the understanding of the subject, so that once we follow it up with other lectures on nuclear strategy, nuclear policy and nuclear deterrence, etc., it will be much easier to understand once this foundation is laid. Nuclear weapon is a complex system, and there are several steps involved in the preparation of nuclear weapons, starting from the prospecting and mining of uranium to the ultimate fabrication of the device. Once we follow up in the further details, I think we'll be able to explain individual steps which are involved, and there will be clarity on what all is included in the preparing or manufacturing of a nuclear bomb. The physical infrastructure required to build a nuclear weapon is, in general terms, called nuclear fuel cycle. And nuclear fuel cycle starts, as I said, from first of all discovering the reservoirs of natural uranium, then mining it, refining it, and then a conversion of this uranium into uranium oxide. Up to that, then it's a common portion of the cycle. And then it takes two routes, which we'll discuss separately. Also, one is the uranium route and other is the plutonium route. And then the facilities involved in this, for instance, in the uranium route are the enrichment facility, and then the fabrication of uranium enriched uranium pit. And then after testing and designing the remaining part of the weapon, then we move on to the actual weapon itself. While on the plutonium side, after the processing of conversion of uranium, then we go to the fabrication of fuel. That fuel is fed into the research reactor, that is also called the production reactor. And the burnt fuel from that reactor is taken out and taken into the reprocessing plant, where plutonium is chemically separated from uranium. Then that separated plutonium is converted into plutonium pit, and then rest of the parts of the device, they are incorporated, and finally we have the weapon. Now, in the uranium route, we just need the major facility we require here is the enrichment plant. And there are various ways of enrichment, starting from the gaseous diffusion process to the jet nozzle separation to laser separation to the gas centrifuge enrichment process. In Pakistan's case, our program is based on the gas centrifuge enrichment process. It's a one of the modern techniques, and it is very economical in terms of the expenditure of energy, because gaseous diffusion plants requires 10 times more energy than the gas centrifuge plant. So the major facility in this case is, first of all, you have to convert that uranium oxide, which is also called yellow cake, into uranium hexafluoride by mixing fluorine gas into the uranium oxide. Then that uranium hexafluoride gas is fed into the gas enrichment facility, and at the end you get enriched gas, which is then converted into solid, and then you manufacture the uranium pit for the weapon. So that is the way you go about. In case of plutonium, up to the initial steps of conversion of uranium into yellow cake, these are the common steps, but then onwards you have to then fabricate fuel pellets, which are then fed into the reactor, where they are burnt. And if you are intending to produce weapons, then you remove that fuel at low burn up. That means you do not burn it fully, you just take it out rather quickly, and then that material also contains plutonium besides the leftover of the uranium fuel. That is then chemically separated into a reprocessing plant. So in this case, there are two major facilities required. One is the research reactor or production reactor, the other is the reprocessing plant. So these are two major facilities, and from there on, then you convert that plutonium, separated plutonium, which is in the liquid form, into a solid, and then fabricate a plutonium pit, and then associate it with the rest of the components of the device, and then you have a nuclear weapon. It depends on what all facilities do you have. For instance, once we started our nuclear weapons program, the preferred route as far as Pakistan Atomic Energy Commission was concerned was the plutonium route. And that is why we went into a deal with the French government to acquire a commercial reprocessing plant, and the logic for that was that since we were expanding our nuclear power program, we needed to reprocess the fuel so that it could be reused, and we could excise economy. And then the idea was that once we start operating that reactor, obviously material generated by that reactor that reprocessing plant could not be used for weapon purposes because of the very strict trilateral safeguards between France, Pakistan and the IAEA. The idea was that after gaining experience in operating that plant, the facility will be replicated, and then Pakistan will be able to produce plutonium. Obviously, you needed also to design and build a plutonium production reactor. So that program, obviously, because of the cancellation of the reprocessing deal, that was no more feasible, and then there was also no production reactor available at that time. Therefore, we had to then go for the uranium enrichment route. In India's case, since they had Cyrus reactor, which was a CANDU type of reactor which was producing plutonium, and they also had a reprocessing plant which was inaugurated in early 1964. So they had all the components of the plutonium route, so they followed that route. So it depends on what kind of fuel cycle facilities are available to you. At present, Pakistan has facilities for both routes, and we are following for both routes. Now, nuclear bomb is a complex device. The main component in this is the fissile material core, whether it is plutonium or enriched uranium. And enriched uranium, once we say enriched uranium, it is 90% or above of uranium-235. We have already discussed the process of achieving enriched uranium or plutonium. But besides that, you need to have a certain quantity of these fissile materials, which is called the critical mass, because without that critical mass, a sustained chain reaction cannot be achieved. But if you have that critical mass, then it is also not very safe to have it there. So you have this mass at less than critical level. Then you have various layers of materials around it. One is the conventional high explosive, and that is designed in a way that it is in the form of concave lenses, and the explosive wave which is generated, it is focused inwards so that it can compress the fissile core and make it into supercritical. We know there are three conditions which determine the size of critical mass. First of all is its purity. So if it is 90% or above enriched uranium, and similarly how pure is the plutonium. Second is density, how densely packed it is, and third is its geometry, which shape it is. It is spherical or square or cylindrical. So ideal is spherical. But in the sphere also, if we increase the density, the size of the critical mass can be reduced. So once we compress it with the simultaneous explosion of the high explosive lenses around it, then it is compressed to a much smaller size and the density is increased. Built into that pit is also a neutron source, which at that time also then starts emitting neutrons, which cause fission, and each fission then releases 3 more neutrons and a large amount of energy. So those 3 neutrons then they move on and split other 3 atoms, and the process goes on until there's so much of energy is built up that the device itself blows up. So the purpose then is to keep the system functioning for as long as possible, because the more series of chain reactions happen, the more output we will get. More material will be utilized and the greater kiloton explosion we will get. So to do that, then we add to it a layer of uranium, a normal natural uranium, because it's a heavy material, so that creates a kind of inertia and slows down the process of blowing up of the device itself. Then we have beryllium reflectors also, which make sure that the free flying neutrons are not lost, they are reflected back into the center of the device where the fission process is taking place. So this is how the fission bomb works. But then there are the other types of bombs. Those are called the fusion bombs, or there are other names also. They're called hydrogen bombs. They're also known as the thermonuclear bombs. Those are more complicated devices because they are 2-stage weapons. The first stage is also called trigger, which is essentially a small fission device which creates enough energy which enables the 2 lighter atoms of the isotopes of hydrogen, that is deuterium and tritium, to fuse together, and that fusion generates very large amounts of energy, which are hundreds of times or more than the energy generated by the fission weapons. But it's a complicated device. As I said, it has 2 stages. The first stage has to work efficiently to enable the second stage to work, and once both stages work, then you get the desired results. We know that in 1998 India claimed to have tested a thermonuclear device. Its first stage worked, but the second stage did not work as designed, and that is why the yield was much lower than planned, and that is why it is called that it was a fizzle. Now nuclear weapons create different kind of effects, and there are different kinds of effects also because of the type of explosion. One is the ground burst. If the weapon is dropped on the ground, it will create a pit and then blow up. And with that, a lot of dust will be kicked up. Dust and debris will be kicked up, which will all get contaminated, and it will go up in the form of a mushroom cloud, and then those contaminated particles then keep falling down, and they will go as far and wide depending on the direction and speed of the wind. It can be carried very far if the wind is strong, but otherwise they will keep falling down, and that process continues, and wherever they fall, then they contaminate that area as well. So it's comparatively, you can say, a dirty bomb in the terms of creating this contamination if it is a ground burst. Ideal, it is a low air burst. And low air burst is that once the weapon is blown, it is not touching the ground. It is higher than the ground itself, and the fireball which is created around it, it is barely touching the surface of the ground. So that is low air burst, and there can be high air burst also, but low air burst is the ideal because it gives you all the effects. The first effect is that it gives out a very strong pulse of light, which is so strong that even the sun pales in comparison, and anybody looking towards that, the eyes can be burnt and it can cause blindness. But that is short-lived. Then a lot of heat is generated in the form of fireball. That heat wave travels in all directions from the point of detonation, which is called ground zero. It goes around in all directions, 360 degrees, and anything coming in its way, if it is a combustible material, it will catch fire. If it is wood, plastic, cloth, anything related with the let's say the petrol, oil, lubricants, etc., they will all catch fire. Even the wooden houses, structures, they will catch fire. Any person in that vicinity will get burnt. There will be very serious skin burns. And then this also keeps dissipating after some distance. It loses its energy and then it ends. This is a short-lived phenomena. Along with this, there is a very strong burst of radiation. Alpha, beta and gamma particles. Alpha, beta particles do not do much damage because they do not have much penetrating capability. But the gamma rays, they can penetrate intervening surfaces, and they can contaminate the area, and anybody in the vicinity of the bomb can get affected, can have radiation sickness, and it can have long-lasting effects. People who absorb large doses of that radiation can die instantly, or some people can die after a few days or months. And then if you have absorbed the radiation which is not sufficient to kill you instantly or in a short time, it will have a long-lasting effect in terms of increased probability of cancers, and also it also damages your genetic system, which then is carried on to the next generations. Then you have because of this heat which is suddenly generated, and it goes up in the form of that cloud, and the heat waves goes out, and then there is a vacuum created at the ground zero, which pulls in winds from all directions at very high speed, at 100 miles or even more than that, many hundreds of miles per hour. And that strong wind also then demolishes buildings and houses and structures, trees, etc., whichever thing comes in the way. So all these combined, the very bright glow of light, then the heat wave, the radioactive burst, then this blast wave, all these combined together cause a destructive effect depending on the size of the explosion within a radius of anywhere from 3 to 5 kilometers with a normal standard bomb to even more in case of the thermonuclear bombs.